test bench framework on fully automated register tests of numerous IPs in SoC. Abstract. The exponential increase in transistor density has escalated the design complexity of the SoC, leading to a longer verification, especially as the number of integrated IP rises. Verification engineers spend a significant amount of time creating and maintaining the numerous IP access test bench. Verification engineers face the challenge of creating and maintaining the numerous test benches, which is time-consuming and increase their workload. Moreover, specification and maintaining the numerous test benches, which is time-consuming and increase their workload. Moreover, specification and exist in the various forms, such as natural language or specific format, can be ambiguous and sometimes challenging for verification engineers to interpret. Additionally, verification holes may arise when verification engineers fail to recognize continuously updated specification. The verification holes increases the likelihood of the potential SoC bugs. This paper introduces a framework for automatically generating IP register test benches from the given specification, so that the framework aims to reduce the potential SoC bug occurrence rate, elevate the workload of verification engineers, and improve verification efficiency through the test bench generation process. The ultimate goal is to shorten the verification TAT in SoC project. Chapter 1. Background. Over the past few decades, continuous advancement in process technology have led to an exponential increase in the transistor intensity per chip. From a verification perspective, this trend indicates the integration of the numerous IPs into SoC has heightened the design complexity, thereby increasing the time required for verification. However, as the numbers of integrated IPs increases, the time required for verification can increase regardless of the design complexity. For example, the number of IPs increases, the engineers need to create and maintain the board test benches for SoC level register tests, such as the read and write test for each IP. Maintaining a large number of the test benches is relatively time-consuming, which can impose a burden on engineers. SoC verification starts with the verification engineers interpreting and understanding the SoC specification. The specification can exist in the various forms. For example, it could be a hardware description, word format, or an Excel format containing various connection details. It can also exist in the form of the emails of chat messages and even verbal. The verification engineers must understand and interpret the various specifications in order to create verification scenarios. If the verification engineers interpret the specification or the specification itself is incorrect, there is possibility that inaccurate the verification scenarios may be created. As a verification using inaccurate scenarios undermine the reliability of the verification and can lead to an increased frequency of bugs. For this reason, creating accurate verification scenarios is a critically important factor. So the challenging is that both the specification and verification scenarios are generated by the human. This implies that there is always a possibility of issues arising due to the human error. For example, issues may arise if specifications inefficiency details, or if the verification engineer is aware of the updates or changes made to a specification. These challenges are among the significant hurdles as modern SoC verification. While methods such as regular reviews of a specification and live verification scenarios can help address these issues, they are not a fundamental solution. This is because the reviews are also conducted by humans and thus still subject to the human error. Moreover, reviews can be time-consuming. In some cases, the test bench may need to be updated to align with the modified specification, which can further add to the time required. These are insufficient inefficiencies that arise due to the human error. Test bench modification, in particular, can occur frequently due to the frequent specification changes common in early stage of the SoC project. This can be considered unnecessary work and contribute to increased fatigue for verification engineers. Moreover, generating all test benches from the specification can be challenging. If the specification is ambiguous or written in natural language, making it difficult to parse, test benches generating them may not be feasible. Additionally, parsing the specification to generate a small number of the test benches may not yield results that justify the time invested. Consequently, an ideal case for the approach would require specification to follow a consistent format and allow for generation of the large number of test benches. In this paper, register access test was selected as a suitable case. This is because the register set tests have a predefined list of IPs to be tested. A number of test benches required to significantly large. Register access tests for IPs are the most fundamental and essential for test during the SoC verification. These tests are relatively straightforward in terms of scenario's complexity. This is because they mostly involve sampling, adapting the register, and read and write operations. However, performing the DG test is essential and highly important during SoC verification. This is because conducting these tests ensures accessibility to the internal registers of the IP, which is necessary for performing more complex tests. However, managing the test benches for this can be time-consuming. As mentioned earlier, a test bench is needed for each IP, and frequent specification changes lead to a frequent modification of the test benches as well. Moreover, such test benches are not well suited for use across the SoC project, as the specification for IPs can vary significantly between projects. If the register access test bench can be automatically generated from the given specification, it will significantly reduce the verification engineer's workload while also shortening the verification TAT. This paper introduced a framework for generating register access to test bench using the given specification. This framework aims to drastically reduce the time required for register access testing. Chapter 2 is a proposed method. The test bench framework consists of the 5 components, including specification control collectors, test bench generators, test executors, debugger, and reporter. Each component is based on the Python script, while the reporter was developed using the Go language. The reason the reporter was developed in Go language is that handling the large volume of the test result requires a fast response, and Go was deemed more suitable for this purpose than Python. A. Specification collector. The specification collector gathers the necessary specification for generating a register access test bench. The primary specifications to be collected are in the list of the IPs to be tested. To collect the IP list, the collector parses the IP-XACT XML format files for use for SoC integration. The SoC address map specification and the UVM universal verification methodology register model specification. The reason for parsing these 3 types of specification is to detect potential errors in the specification, which would be impossible if only a single specification were analyzed. Additionally, by exploring the multiple specifications, the integrity of each specification can be guaranteed, and cross-checking can be performed. The reason for collector parses the 3 specifications mentioned earlier is follows. First, from the XML file, the name of the IPs integrated into block of the SoC can be obtained. It's also a file format that is advantageous for Python to parse. Next, from the SoC address map specification, the collector can obtain the list of the IPs included in each block of the SoC and the base address information assigned to each IP. The address map specification file is typically an Excel file, which is convenient for Python to parse. Finally, from the UVM register model, the collector can obtain the list of IPs within the SoC. The UVM class handler names and the base address information for each IP. The SoC verification process mainly takes place in a UVM test bench environment. Therefore, the conduct a register test and the UVM register class handler corresponding to each IP must be matched. For this reason, the collector explores the UVM register model. After exploring the three specifications, the information obtained from each specification is compared. First, the obtained IP lists are compared to check for any mismatched IPs between the three lists. If any mismatched IP names are found, it is considered a specification bug and an error log is generated to allow the verification engineers to identify it. The same comparison is made for the base address information of each IP, and if any mismatches are found, an error log is generated. In addition to the basic read and write test during the register access test, checking the security attribute can also be performed. The security test verified whether the RTL implementation aligning the security specification by checking the access permission based on the different security levels between the master and IPs. For example, if an IP is set to secure mode, non-secure master should be not able to access it. The security specification is also managed in a structured file format, and in the case of SoC, TZPC, Trust Zone Protection Controller, a table can be an example of this. The collector also explores the security specification and collects the security specification information for each IP. When the benefit specification collection is completed, the collector generates YAML format file. A file contains the collected specification information for each IP. This YAML format file is used later during the test bench generation process. Figure 1 provides an example of the operation structure of the specification character for IP-A and the generated YAML file. The generated YAML file format file is used as an input file for the test bench generation. Figure 1 is an example of the operation of the specification collector IP_A. A IP-XACT XML. B. SoC address map Excel file. C. UVM register model class. Specification collect. D is a security specification table, and E is the generated YAML format file. B. The test generator. The YAML format, the file contains all necessary information for creating the register access test benches for all IPs within the SoC. The test bench generator uses the given YAML data as an input to generate register access test benches for each IP. The Python Jinja2 library used in this process. The Jinja2 library leverages template to render and is well suited for generating a large volume of test benches efficiently. However, it requires the template be predefined, which may take less suitable for test benches that undergo the frequently changes. However, the structure of the register access test bench is simple, consisting mainly repeated read and write operations, making the test sequence straightforward. As a result, changes to the test benches are minimal. Therefore, it's suitable for Jinja2 template-based rendering, as changes to a template can be minimized. Table 1 shows a Jinja2 template used to generate register access test benches for individual IPs. To facilitate the efficient template management, template macros were utilized to establish the overall template structure. Table 2 shows the Jinja 2 template macros. The template macros are set of a variable that are updated for each IP. Table 1, the template for the generation of the individual IP register test benches. Table 2, the template macro. C, the test executor. Once the test bench has been successfully generated, the next step is used to generate the test bench to perform an actual IP's register access test. While the verification engineers can perform the test manually, the sheer volume of the test benches often exceeding 100 makes the approach highly efficient. To resolve this framework, extend each functionality to include test execution. After generating the test benches, the test executor begins with the duty compilation and performs the regression testing for the register tests automatically. The debugger. Errors may be during the register access test. Errors can arise from the various causes, and verification engineers must debug them to ensure the test pass. For example, a master might receive an unexpected error response while reading from or writing to a register of a specific IP. Other issues, such as bus hang-on mismatches between the write data and read data, could also occur. These errors may be requires varying the amount of the debugging time depending the skill levels of the verification engineer. Sometimes they are solved quickly, but at the other times they can consume a significant amount of time for debugging. Moreover, the increasing complexity of the SoC architectures tends to further extend the time required for debugging. As a result, the more debugging time is reduced, the easier it comes to a shortened verification TAT. And the test bench framework aims to reduce debugging time by building a basic level internal debugger and utilizing the BTS bus trace system based debugger. In UVM-based verification environment, errors are reported as a UVM error. Additionally, the verification engineers can include the custom messaging when printing UVM_error to the simulation log. This means that the test bench can attach text to the UVM_error and print them in a simulation log, enable the identification of the errors using these tags. The debugger includes a solution for each of these error tags. If an error, the specific tag is using printed in the log, a corresponding solution is provided. The solutions are predefined test benches for these errors, which are predictable in nature. However, unexpected errors may occur during simulation. Design-related bugs can lead to the bus hangs or unexpected bus responses. Since the type of the error are not well-defined, solutions cannot be provided for them to easily debug such errors. The framework utilizes the BTS. BTS can pinpoint the exact point of the problem, such as bus hangs and error responses. BTS is implemented as a UVM monitor with a test bench, and it is activated through the VIP callback mechanism. If a time error callback occurs, it identifies as a bus hang, triggering the response BTS debugger. Similarly, if an error response is callback indicated the error response, the relevant debugger is invoked for debugging. Once debugging is completed, the issue points are printed in the simulation log. As a result, verification engineers can accurately identify the issues point related to the bus hangs and the error responses. Figure 2 illustrates the operation of the framework debugger for errors that occur in the simulation log. Three types of the error logs are displayed, including predefined errors with the error solutions, error responses, and bus hang error logs. In the case of error responses and bus hangs, the debugging results from the BTS are also included. A. The predefined error log and error solutions. B is the error response log and debug registered by BTS. C is both the hang log and log registered by the BTS. Figure 2. Overall operation of the framework debugger for errors that occur in the error simulation log. The E, section E, report. If 1,000 of the simulations and successful without errors, it will be quite difficult to there is no way to check this. Additionally, checking the result of each simulation one by one is very inefficient. In other words, a platform that allows for a quick overview of a simulation result is essential. Through the reporter in the test bench framework, battlefield engineers can view the results of the simulation at a glance. The reporter was developed in the goal as it needs to handle large amount of the simulation result data and delivering high responsiveness, which is relatively faster than a Python. EDA vendors provide tools for reviewing the simulation results. However, these tools appear to be over-specified for registered access tests, so the reporter was developed. The reporter provides three types of views. The first view displays the registered test results for each block within the SoC, including the pass or fail status and the pass rate for each block. Figure 3 shows the first view that a verification engineer see when they call the report. This view displays the entire regression suite list along with the test status for each entry. Figure 3 is the first view of the reporter. The engineer scan the regression suite list to the few registered access simulation results for a specific block. Figure 4 illustrates the results of the registered access test regression for block F. This view provides an overview of a tested result for IPs included in each block at a glance. Additionally, if the test result for a specific IP fails, it is possible to identify the type of the error that occurred. Figure 4 is the registered access to regression result of block F. The Ethernet SoC project. The RTL corresponding to DUT is typically managed using the version control tools such as Git or Perforce. Additionally, the RTL is released to the verification team at a later levels with a specific level. In principle, the simulation must be performed for all testable scenarios which time the RTL is released. However, this is often impractical due to the limited resources of verification engineers and the relatively short timeline of the SoC project. If the estimate tailored to the release of RTL labels is automatically generated, simulations are executed accordingly. This goal could be partially realized. The testing framework is automatically triggered by using the RTL label or released as an event. In this paper, the framework is triggered using the P4 trigger command. One of the purpose command as an event. If the RTL is managed with a Git, the framework can also be triggered using Git actions. The P4 trigger is a command that defines and executes the script when the specific actions are performed in a designated directory. Through this, the test bench framework is automatically executed each time the RTL label file is registered to the purpose. However, there are several prerequisites for automatically executing the framework through the P4 trigger. First, the RTL labels files must be periodically created in predefined, agreed upon paths. This is executed the command requires specification directly for the event trigger. If the path is too broad, the framework may be executed unintentionally. Additionally, the RTL label files must follow the predefined naming patterns. This is also prevent unintended triggering of the framework. When an RTL label is a file committed to a specific path, the framework operator to generate an IP register, access test bench, and create a Perforce change list for the related test bench files. This process is repeated each time an RTL label is committed to using the IP-XACT project timeline. As a result, for each RTL label, the the IP register access test bench is automatically generated to the matched label, and the simulation is also performed automatically. In other words, the framework implements full automation for IP register access testing in SoC project, from the test bench generation and simulation execution to debugging, without the need for invention for verification engineers. Figure 5 illustrates the overall working flow of the test bench framework. This is the framework. Figure 5 is the working flow for the test bench framework. Test bench framework. Artillery event people trigger, specification collector, test bench generator, test executor and debugger and reporter. Chapter 3 Result. Table 4 shows the total number of the IPs per project, the number of IP register access tests related to them, and the total number of the tests performed per project in the 5 recent SoC projects conducted by the company. Although there is a variability, the total number of the IPs and the test across the project, it can be observed then average. So approximately 35% of the total tests are related to IP register access. The region for the number of the tests is significantly higher than the number of the IPs that, in addition to basic register access tests, there are also security related tests. Furthermore, the number of IPs on each project matches to the IP number of the IP register access test benches. Table 4, the proportion of IP register tests relative to the total number of the tests. As a result, the test bench framework can cover approximately 35% of the test benches per project on average, and it also eliminated the time required for maintaining these test benches. Additionally, the register access test can be automatically executed for each RTL label, which is periodically released for every project. This is significant. They can be proactive prevent verification hold for IPs with the specification changes that verification engineers may be aware of. Furthermore, since tests are executed for each label, the framework can also serve as a sanity check for IP register access. The conclusion: through the IP register access test bench framework, approximately 35% of the tests related to each SoC project can be automatically generated with their language test benches. In addition to generating test benches, the process can be the automated simulation runs and debugging in the event of the errors. This is significant in that they reduce the time spent for performing the IP register access test and maintain the test benches, thereby efficiently shortening the verification TAT. This enables effective reduction of the verification time, which is crucial as SoC architectures become increasingly complex, leading to the longer simulation times in line with the cadence SoC, with the modern SoC developed trend. However, the true significance lies on the fact that the framework automatically performs the sanity tests for IP specification changes that verification engineers may not be aware of, allowing for early detection of the IP bugs. This allows for early improvement of the verification quality and enables more efficient time allocation for verification engineers. Reference is like this. And then, today I read this paper, Test bench framework for fully automated register tests of numerous IPs in SoC from DVCON2025.